So we are going to complete this chapter on rings of polynomials with a closer look at the evaluation homomorphism and trying to redefine a solution of a polynomial. And also we'll do some simple examples, simple problems on this section. So the idea is when you want to solve a polynomial equation like, let's say, 4x squared minus 3x plus 2 equal to 0. We write the polynomial on the left hand side and 0 on the right hand side and trying to find the value of x. But when we define the rings of polynomials, we call this one as indeterminate because we know that the value of this x may not be in the same field or ring of the coefficients. So we are going to redefine the idea of solving the equation using using evaluation homomorphism. So let us define the homomorphism first. Let F be a field and F is a subfield of another field. Then define a map phi alpha from from f of x to E for some fixed alpha in E by phi alpha of this is actually the ring of polynomials with coefficients from the field F. So let us write it as f of x is equal to a0 plus a1 alpha plus a2 alpha square plus dash dash plus an alpha to the power of n, where f of x is equal to a0 plus a1x plus dash dash anx to the power of n. See, though we have defined the polynomial as an infinite sequence of terms like this, eventually what will happen is that polynomial will have only finite number of non-zero values, non-zero terms. So we can always write a polynomial as a finite sequence like this. The definition is on infinite series because to avoid some confusion. But finally, when you start writing the polynomial, you will write it like a finite sequence. So what we are doing here is you are replacing every indeterminate by this alpha and find the value of this. This is a valid function because all ai's belongs to F, and because F is a subfield of E, all these A zeros belongs to E, and alpha is already an element of E. So this finite combination of sum definitely is going to be in E. So this is a valid function. See, this is going to be like this. There is an E here, there is an F here, and alpha is somewhere here, or it could be inside F also. So we are going to define from f of x to this by replacing the indeterminate with the alpha, and that is what this one is. So our claim is, I'm not going to give you all the details of the proof. It is very straightforward. The claim is phi alpha is a homomorphism. Okay? See, the basic idea here is, let us say you take f is equal to, let's say q, okay, and f of x is equal to x square minus 2. Okay, so our f of x is actually q of x, but if you want to find the solution of this polynomial, the value is not in Q, it is outside Q. Let us take R as a extension of Q, or Q is a subfield of R. So what you are going to say here is phi of root 2 of x square minus 2, and that would be C. Of course, this is a homomorphism. I am taking one element from Q of x and evaluating it. This is a general map. Okay, so that is the idea of picking alpha from an extension field. When I say f is a subfield of E, E is an extension of f. Okay, if you want to show this is a homomorphism, there are two things we need to prove. Phi of alpha of f of x plus g of x is equal to phi of f of x plus phi of g of x. That is very simple. So what we will do is let f of x is equal to a0 plus a1x plus dash dash a n xn, and g of x is equal to b0 plus b1x1 b1x plus dash 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 br xr or bm xm, right? So how do you add? See, you take if n is greater, let us assume that n is greater than m, then what you do is you extend this one to b0 plus b1x plus dash dash bm x to the power of m plus 0 x to the power of n plus 1 dash 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 0 x to the power of n. So this is going to be our bm plus 1 dash dash bn. So how do you add this? F of x plus g of x is equal to c0 plus c1x plus dash dash cn xn, where ci is equal to ai plus bi. And so it is clear that See, if you take this phi of alpha of f of x plus g of x is equal to phi alpha of c 0 plus c1 x plus dash dash cn xn, and that is equal to c1 plus c0 plus c1 alpha plus dash dash cn alpha to the power of n. And phi of alpha f of x, phi of alpha of f of x, plus phi alpha of g of x is also going to be it's going to be a0 plus a1 alpha plus dash dash an alpha to the power of n plus b0 plus b1 alpha plus dash dash bn alpha to the power of n, and that is equal to c0 plus c1 alpha plus dash dash cn alpha to the power of n, and that is equal to phi of alpha f of x plus g of x. So I will give the second part of the homomorphism as an exercise, and that is we need to prove that phi of alpha x times g of x is equal to phi of f of alpha, f of x times phi of g of x. This I am going to leave it to you as an exercise. Now, our idea here is denote f alpha of f of x is equal to f of alpha. This is how we normally denote f of alpha, and that is actually the image of f of alpha under this homomorphism. So for f of x in f of x, if there exists an alpha in E such that phi alpha of f of x is equal to 0, then we say that alpha is a 0 of f of x. Alpha is a 0 of f of x means f of x is a polynomial, and when you solve the polynomial, one of the value of the indeterminate is alpha. So this is another way of saying the solution of a polynomial. Alpha is a 0 of f of x. In this case, alpha does not belong, need not belong to the field of coefficients of the polynomials of f of x. Now let us do some properties of evaluation homomorphism. So our evaluation homomorphism is from phi alpha from f of x to E, where f is a subfield of E and alpha belongs to E. See, so it is going to be like this. E, f and f of x is here. This is our phi of alpha. Alpha is somewhere here. So phi of alpha takes x to alpha. Every x to alpha, because this is a polynomial in f of x. So replace x by alpha. So this is f alpha takes x to alpha. And if a belongs to f, if a belongs to f, phi of alpha of a belongs to f, meaning a is a polynomial, is a constant polynomial in f of x, and that is equal to a. And that implies phi of alpha is the identity map on f, always, whatever be the value of alpha. So actually f is a subfield of f of x, not subfield. Actually this is not a field, so you can say f is a subring of f of x. If you take f as a subring of f of x, then phi alpha maps f to f. So this is another property. So this is property number 1. This is 2. Let us do some very simple examples on polynomials over a field. Let us take a finite field. Let us take let f of x is equal to 3x square minus 2x plus 6, and g of x is equal to 4x, or probably let us take 6x plus 2. And I'm going to consider these f of x and g of x to be in C7 of x. C7 is a finite field. So f of x and g of x, these are not in Z but in Z7 of x. So we want to find out f of x plus g of x, and that is going to be equal to 3x square minus 2. What is minus 2 in 7 of x? This is C7. Minus 2 in C7 is 5, right? Because 5 plus 2 is 0. So minus 2 is 5. So this is actually plus 5x. Plus 5x plus 6x, 7x. So under C7, this is actually 4x. This is going to be 5x, because the additive inverse of 2 is 5. So you can write it as plus 5x. 5x plus 6x is 11x mod 7 4x, plus 6 plus 2 8 mod 7 is 1. So we can write this one as 3x square plus 5x plus 6. Both are same in C7 of x. So f of x times g of x is equal to, we will write it like this, 3x square plus 5x plus 6, 6x plus 2. So what we have is 6x square plus 10x meaning 3x, 12 meaning 5. Then this is going to be 18 18 under 7 is 4x cube. This is 30x square, that is 2x square, then plus 36x, that is x. So 5 plus 4x plus 8x square, and that is x square, and this is going to be 4x cube. So this is 4x cube plus x square plus 4x plus 5. So we are taking the polynomial over a field other than z of x. That is what I want to show you here. Now let us do another example. Find the number of polynomials of degree less than or equal to 2 in C5 of x, meaning quadratic polynomial. We are looking for only quadratic polynomial or less. So the total number of polynomials. So any polynomial of degree less than or equal to 2 in z of 5 of x can be written as ax square plus bx plus c, where a comma b comma c belongs to C5. This has to come from C5, and that means the total number of such polynomials is 5 times 5 times 5, 125. There are only 125 different quadratic or less of polynomial of degree less than 2 in C5 of x. In Z there are infinite, but in C5 there are only 125. So let us complete this chapter with one more problem. So let R be a commutative ring. And T be a non-empty subset of R closed under multiplication. And 0 does not belong to T, and T does not contain any 0 devices. Of R. Then the partial ring of coefficient Q of RT has a unity even if R does not. It's a very simple problem. So let R be a ring and T is a subset of R. 0 does not belong to T. Okay. Now what is Q of RT? It's a partial ring of coefficients, means this is equal to A comma B, the classes containing A comma B ordered pairs, such that A belong to R, B belong to T, and B is different from 0 because T is, we don't need to put that condition here because T does not contain 0, and the relation is defined as A is related to C comma D if AD is equal to BC. So we need to show that there exists a unity in this. There exists unity in this. There is only one unity, and that this ring of partial ring of quotients has the unity. So let A belongs to T, and that implies A is different from 0. Then the claim is the class A comma A is the unity of Q of RT. How do you prove this? We'll see. Let A, B comma C belongs to Q of RT. Then we multiply A comma A times B comma C, and that is by definition is AB AC, and that is actually equal to B comma C, because ABC equal to ACB. This is a commutative ring. So these two classes of equivalent classes are same, and that means you are multiplying this element with BC and equal to BC, which means that this implies A comma A is the unity of Q of